Everybody, you have a cubic equation. This is kind of a standard problem where actually directly finding the roots and then substituting those roots into this expression that we're trying to evaluate would be almost impossible for a person. Now, because a, b, and c are the names of our roots for this problem, each of those roots corresponds to a factor. Okay, so x minus a is a factor, x minus b is a factor, x minus c is a factor. All right, and the approach we'll take will be to expand this and then see what we can get from these coefficients of 13, 14, and 15. Okay, so that's what we do here below. If you expand this out, and again, this would take some time and is a little error prone, but you have minus the sum of the zeros as the coefficient of x squares, and then you have the pairwise product summed up is the coefficient of x, and you have minus the product of the zeros sitting out here, okay? And so what we can conclude right now already is that you would have a plus b plus c is equal to negative 13, and that's by inspection. Again, folks, you literally equate this exponent right here with this constant exponent of 13. And you get the sum of the zeros equals to negative 13. And in a similar fashion, you would get AB plus AC plus BC. And again, just a direct comparison here. This is the coefficient of x. The coefficient of x here is 14, so this would be equal to 14. Okay, and then finally you would get, just by comparing this constant term with 15, you would get a, b, c is equal to negative 15. So we don't know the roots, but we know these various combinations. These are called elementary symmetric polynomials, by the way. This would be a degree 3, this would be a degree 2, and this would be considered a degree 1 elementary symmetric polynomial. So what did I say? AB is equal to minus 15. Right? Now, so this begs us to simplify this expression in terms of these three ESPs, elementary symmetric polynomials. Okay, and so the rest of this, y'all, is just a ton of algebra, and I'm certainly not going to. A big discovery for me was to rewrite this, okay, as this. And y'all, this part right here is just a common denominator. Going from here to here, we got a common denominator routine going here. It's all that happened right here, folks. Again, going from the given to this statement right here, it involves just common denominator work, multiplying this one by c, and then this one by ab. Okay, is all that happened there. Why we were motivated to do that because we know that ABC is equal to negative 15. So you see, we're kind of towards our answer already, right? We know that ABC itself is equal to minus 15, but we've got to get the rest of this resolved. And we anticipate getting it resolved in terms of these elementary symmetric polynomials, okay? And again, y'all, it's mainly algebra. This was motivated because when you write this greened out expression like this, you get a common factor of a plus b here, okay? And the rest of this is just bash it out, dumbassing algebra, okay? Dumbassing is a term used in the Olympiads, by the way. All right, so again, I won't spend much time talking to you about the algebra. It's all something you can discover. I factored the a plus b out. That was the motivation for writing this like a plus b quantity squared, okay? And I'll proceed without too much commentary here. The algebra was kind of, like I say, it was a bash sort of, you know. But again, we got to a point where we can recognize what this is going to be equal to. You see, we have a common binomial factor here, or trinomial, that's equal to one of the ESPs, right? And so you can see here, if you factor AB plus AC plus BC out of the numerator, okay? And again, this is present. The way that all the multiplies went out, it's out of order, but addition is commutative, fortunately for us. All right, and so you would get right here a plus b plus c. You see you have the a plus b here, and then the c here, and it's just the distributive property. Okay, going on here. Okay, all over ABC. All right, folks. Now I've already forgot the numbers, but we see this is a remarkable success here because we know all of these values. We recognize all of these parenthetical expressions as coefficients, more or less, notwithstanding the sign, right? So what was it? So that would be minus. This would be minus 13. Okay, minus 13. And what else? 14 minus 13 times 14. Okay, in ABC I think was minus 15, right? Yeah, ABC is minus 15, so we get this going on. Yeah, it looks like there's no common factor. This is a prime number. This has 2 and 7. So this is not going to reduce, right? You don't have any, you don't have to multiply this out or anything because it's not going to reduce. I guess it would be more professional. Let's see. 10 times 14 is 140. 3 times 14 is 42. So I'm getting 182 over 15. I didn't make a mistake there. And again, you know that this is a reduced fraction simply because the good old prime. We have a 3 times a 5 right here, a 2 times a 7 right here, and a 13, which is prime. So there's no way this is going to reduce. The only mistake I could have made is if I didn't multiply 13 times 14 right, but I think I got that right because it's 140 plus 42, which is 182. So that is our answer, folks. And again, just show you how much work we saved is onerous and laborious as this looked. Try to use Cardano's formula for the cubic. You get these awful looking nested zeros. They may be complex, they may just be nested radicals, irrational numbers, and then trying to substitute this back in would be burdensome. It's an arithmetician's nightmare. Okay, but anyway, the answer to this is 182 over 15. Let me come up here and write it. I don't do that all the time, but I'll do it this time. So this is equal to 182 over 15. Again, a lot of algebra got the job done on this one. Okay, thanks for being.